Hi, everyone. Welcome to the 33rd International Congress of the Materials 2025. My name is Maricruz López, and today I am excited to present our research titled Effect of Gamma Irradiation in Hydroxyapatite. Well, I show you the poster and start with the explication. Okay. Well, everyone knows that hydroxyapatite, or HAP, is a critical material in biomedical applications, such as in bone implants and drug delivery systems, due to the biocompatibility with structural similarity to human bone. So, however, its behavior under gamma radiation, a common sterilization method, remains unexplored, especially at low doses. Now, in this study, we synthesized pure hydroxyapatite and carbonate hydroxyapatite and exposed them to low dose gamma radiation, 20 to 200 CKG, to analyze structural and chemical changes. Our goal was to evaluate their potential as dosimeters and understand their stability under irradiation. Well, let's dive into the methodology and key findings. In the case of experimental details, we synthesized hydroxyapatite and hydroxyapatite doped using a co-precipitation method. The precursors include nitrate calcium, phosphotamine, and ammonium bicarbonate with the pH careful adjust to 10 using ammonium hydroxide. The samples were then pelleted and irradiated with a cobalt 16 and source with doses ranging from 20 to 200 CKA, incremented by 20 CKJ per step. They characterize the effects. We employ Raman spectroscopy to detect radical formation. FTR spectroscopy, as you can see in this spectra, and the SEM for morphological examination. And finally, we will use photoluminescence, but for this propose and know for a condition that we can obtain these results. So the principal information of this Raman and FTR results is that in the Raman spectroscopy revealed that those above 180 CA induced chains associated with carbonate radicals in carbonate hydroxyapatite, suggesting higher sensitivity to gamma radiation compared to pure HAP. In the case of FT results, images confirm the preserved two significant alterations indicating the gamma irradiation, and this dose doesn't disrupt major chemical in HAP. And finally, in the case of SEM, images confirming the preserved morphology of carbonate hydroxyapatite even post irradiation, which is crucial for biomedical applications where structural integrity matters. These results align, in the case of the conclusions, with prior studies, which report the gamma radiation creates stable defects like carbonate or CO2 radicals in HAP, but our work on nickel highlights the dose-dependent sensitivity of carbonate hydroxyapatite. Our findings suggest that carbonate HAP is more responsive to low dose gamma radiation than pure HAP, making it a promising candidate for dosimetry, a tool to measure radiation exposure. While high dose studies, typical best 1 KHA focus on sterilization or low dose approach opens doors for application like now radiation dosimeters in medical or environmental monitoring, biomedical implants with built-in radiation sensitivity, and drug delivery systems where we can control radiation triggers relapse. And however, further research, especially XRD analysis, is needed to validate the structure crystallinity and the chains and optimize carbonate HAP and dosimetry properties. And well, in summary, we demonstrate that low dose gamma irradiation effects in carbonate HAP more significantly than pure HAP, particular through carbonate radical formation. This paves the way for innovative in biomedical and dosimetric applications. I'd like to thank my collaborations with the technical teams at Watch and Simvestab IPN and funding agencies for their support. Special thanks to Ramirez Martinez Abiu for STEM assistance. And we welcome questions and collaborations to advance this research. Thank you for your attention. And finally, welcome now to the Theory Congress International. And I expect you like this investigation. Thank you for your attention and goodbye.